Hello, and welcome to the explanation of the interior of the spaceship. The spaceship itself is going to be designed and created in its whole entirety as a single um, unit of function. So, the volume weight of the ship will include all of the volume weight of all of the technology which is going to be in the ship. So, the majority of the size of it and the overall volume of the weight of the actual ship itself is going to be the driving force to miniaturize the technology that we have and miniaturize the technology that we have developed into a structural volume of overall weight. It means that the shell of the craft itself is going to be designed to create and build the spaces for the technology to be able to fit into. So instead of creating a ship which is an extra external weight to the overall volume of weight, now we are looking for certain areas of volume of weight to go with the volume of gravity. But we are also looking for streamlining the overall weight volume to be able to get the craft up and out and into the atmosphere, and then outside the atmosphere and into our solar system. So, because we have to work with an overall size and an overall volume of, of known weight to be able to get the craft up and out and into space, a lot of the design structures of the actual shell technology is going to be created inside the shell. So you have an outer casing of the ship's shell, and you will have the interior shell, and inside the interior of the actual ship's shell, there will be design spaces. Inside design spaces, these will be backs of their the backs of their case. So it means that instead of including extra weight into the ship, that we are balancing the overall weight into the volume of the weight of the ship. So half the technology development is in developing front ends of casings that will go with the back ends of the ship's casing. And inside, there will be the technology. So inside the gap that is created will fit all the technology that we desire to be inside the ship. Because the interior of the ship is going to be half of all of the casings that will hold the technology in their design spaces, it also means that the ship itself has to be structurally designed to be able to function inside the open spaces. So everything that we have in the ship's weight is included in the development of the technology that will fit in the ship. Now, there is a certain volume weight that can be added to any vessel. To cut the weight of it down by half, right, is basically fighting the battle of volume weight that will get out into space. Now, there is also a certain volume of known weight which is required and will be needed for certain development structures of a craft. So, we're going to have a cargo space, and there will be volume weight requirements for cargo to fit in the cargo space. There'll also be volume weight requirements for passengers and staff and scientists that will fit in the ship. And then there's a volume weight of technology that also is added to the ship. And all of it needs to fit the volume of the overall weight of the craft. So you can actually fill it with things and then get the thing up and out and into space. Now, obviously, there are two ways of being able to work with a spaceship. You can have one which is not staffed, and you can have one which is basically not, um, uh, that doesn't include any extra volume of any weight. And you can remotely pilot this particular craft, and it will get out into the atmosphere and up into space and back again as a test. So we're going to work with um, developers, and we're going to work with uh, structural designers to be able to create and build the reusable spacecraft. Now, with all the technology of miniaturization and lightweight materials, and also lightweight production of lightweight um, structures, the energy of electricity that I am developing, along with other people on a global scale, when it comes to renewable energies, is all put together as a finished product of design development. Now, there are loads of things that you can do to trim weight, and there are a load of things that you can do to add weight. Now, to trim the weight of the shell and trim the weight of the technology is paramount when it comes to inclusion of extra weight, things like cargo and passenger ship, right? So there are lots of things that we can do. There are materials that we can create, which are lightweight materials and lightweight builds that will build a lightweight product for electrical production. Because lightweight products are for electrical production, and lightweight products designed to be included into the ship's interior design structure, then it means that we also have a casing which is half developed and half designed inside the shell of the ship. We also have another half of a casing which fits over the top of that with the technology inside once it's covered. And then when you look at the overall interior side, once it's covered, and then when you look at the overall interior of the ship itself, is that it's all smooth with the technology inside all of the design spaces. So because it's smooth and also interior detailing for the ship's structure, inside the interior detailing of the ship's structure, you will find built-in technology. You will find built-in technology into the columns of the ship. You will find interior technology built into the ceiling of, of the room. You will find interior technology in a layered space of a gap, which is produced for the structural design of the interior of the ship itself. Now, because it's design spaces to include open space for people to move through, it also means that all of the interior development of the design of the ship itself for all kinds of um, uh, pleasant views of interior, every single little bit of a designed hump or a designed curve or a designed structure which is designed specifically for, let's say, structural strength of development, right, in its actual structure of beamwork development, there will be a density of a thickness, but there'll also be a lightweight structure to it as well. So in certain areas, you will have a certain density of a thickness, and inside the hollow casing, of this design structure framework, which is designed to strengthen the interior of the ship and also designed to strengthen the corridor development, but it'll also be a design structure that will strengthen the outside of the ship itself. So the surface of the ship will have a strength and a development design to it. The interior of it will also be developed and designed, but there also will be gaps and spaces. And in these gaps and spaces, there will be all the technology development that will fit inside these structures. So even though designed for, like a girder in a building where you have the T-shaped girder, you have the space inside, right? Top and bottom. These spaces are going to be used to fit technology in. Now, because of the lightweight structure of the lightweight technology development, it means that the added weight in the actual girder space, right, will not have a massive impact in the overall weight. So it means that all these gaps and spaces will be filled with lightweight technology for electrical energy production. They'll also be developed and designed to cope with managing electrical current and managing electrical flow. Now, we all know that ceramic, when it comes to electrical current flow, is a product which is a resistance and a safeguard for electricity. So, because of the ceramic being the ceramic shell of the ship, we also know that any human that dwell inside the ship of the ceramic development is also going to be safe from electrical currents and from electrical flows and from plasma currents flows and plasma ducts and various other things that we're building and developing for the interior of the actual ship itself. Now, because it's a development for interior design and a development for exterior ship shell for aerodynamics and for overall weight volume and for all other known um, structures that will build a lightweight and functional reusable craft. Now, there are a lot of people that will say that if you build too much into the structure, right, that you're never going to get the thing out. There is an argument point to this. The north and south poles of our planet have areas of what I would call an exit into the solar system. Now, these areas are uh, in our planetary structure of our atmosphere because of the magnetic field. Now, the magnetic field from our pole goes like this, goes like a donut, right? But it's like a kidney shape. So it's all a kidney shape, right? All the way around to the South Pole and then all the way around to the North Pole, right? Because we've got the North and South Pole, right? There is a an opportunity in North and South Pole exits of spaceships, and you ride the volume of the actual magnetic field all the way out to the outside rather than punch it through an atmosphere and punch it through a resistance, right? Where there is the magnetic resistance around our planet, right? The strength of it is roughly round about here. And as you get closer and closer and closer and closer to the North Pole, it becomes weaker. And when you're at the North Pole, this super cool, right, space keeps our North and South Pole in ice and snow. Now, of course, ice and snow would melt, right, in our North and South Poles, right, if there was the relevant heat source to melt it, but it still wouldn't change the natural forces of the magnetic field. The natural forces of magnetic field means that in this area of our planet on North and South Poles, there is an exit point for spaceships of certain weight. Now, if you build a ship with, let's say, a certain weight, but still flies in our atmosphere, right, and is capable of taking off and flying and managing, but isn't capable of exiting through the atmosphere at the stronger points, better to fly the ship to the North Pole area where there is a lighter atmosphere. It's lighter and it's not, and you can get things out into space. So we know that there are 2 points in our Earth's uh, uh, positioning where there is a north and south pole weakness when it comes to overall volume of weight. So we can always get things out into the solar system of certain volumes of weight. So we are dealing now with two volumes of weight. We're dealing with the weight of a volume that will exit from a North Pole position and a South Pole position into space. And we're also dealing with a volume of weight that will exit at the strongest point from the Earth's surface all the way out through the strongest field into space. So we've got two ship developments. We've got one which is designed to exit through the North and South Pole because of the weakness in the atmosphere and the weakness of the strength required to be able to get out, right? And we're working with a volume of weight which will punch it through the strongest point of our resistance when it comes to the atmospheric resistance and into space. So the two developments of the ship design are designed and developed for different exit points. And because they're designed and developed for different exit points, we are now working with two volumes of weight. And we're also working with two volumes of weight which include the volume of technological weight. So for a test, we can exit from a North and South Pole. And for another test of a lighter developed structure, we can exit through the strongest point. And because we can do this in two structural ways of development, it means that the first development, which is always slightly heavier, right, we can use North and South Pole. In the future development of lighter structures of lighter weight craft, we can then exit through the strongest point of our atmospheric resistance. Now, because we're including engines and the development and the interior build of engine weight into the shell technology, so when it comes to the engine development, half of the weight of it is already removed from the weight of the engine and included it into the weight of the shell of the ship. And because we're developing a ship shell that has weaknesses and strengths in areas when it comes to density and thickness and also resistance, we are now creating what is very similar to a honeycomb type structure in the sense of weaknesses and strength. So we're dealing with geometrical shapes and geometrical geometry for interior development. We're dealing with geometrical and geometry for external development of the actual aerodynamics of the craft, and including a lightweight region area of honeycomb type strength in the fields of the structure. So it means that we're going to have lightweight density in certain areas, and then we're going to have thin, dense materials fitting on honeycombed, structured, lightweight material. So it's going to be like a thin layer of dense material, which will have a structural design form of function built into it. And then we have the honeycomb structured in the interior for lightweight build, which is very similar to a bird's um, skeletal structure, right? And then we'll have the exterior, thin density, design developed structure for for specific function, and in between will be all the lightweight material. Now, in this structure, we can run all sorts of things, right? Because it's ceramic, and because we can develop it and design it to a point where it's geometrically smooth and geometrically strong, right? I'm going to shine light through it. I'm going to shine light beams and light structures and all things of light transport through these structural forms inside the ship. So the ship will have naturally formed and naturally um, uh, developed conduits of light transport. So the lightweight material will also have light streaming through it. So it will cover the whole length and breadth of the ship. Then I'm going to have developed at one end and at the other end to receive all this light that is being streamed through the center of the shell of the ship, right? Now, once I've got all this light streamed and kept streaming through the central core of the ship, the diodes on the outside of the ship that are going to be developed will light up or create the ability to be able to build any single thing you want on the exterior. So you can have numbers and you can have lettering and wording. You can have change of colored shells. So you'll be able to shine a color and change the ship's color in its whole entirety and still have black lettering, right? When it comes to the exterior diode type situation that we're creating for the exterior of the ship. Now, it'll all be smooth and it'll all be um, all be developed with various gases that are trapped inside, right? But it will also have a very thin, thick, dense layer which will control the actual surface. And once all of this has been put together, right, it will then hold the interior. So you've got sensors at both ends of the ship, one at the back, one at the front, light streaming all the way through the structure that will activate all of these cloaking type devices on the exterior of the ship. It will also include, right, interior lighting activation. So, because of all these structural energy of light energy streaming through the shell, it will also activate the interior lighting as well. So the sensors on either end one will activate the shell exterior, the other one will activate the lighting interior, but it will also have a connection to for communication pathways in light technology computing for crystal development of crystal communications, of crystal technology in the ship. So the crystal computers of crystal development under crystal processing, right, will also have a connection to all of this light that streams through the ship. And it's the interior of the shell of the ship in which it's all going to be bleeding through and into this honeycombing, right? It will all connect up to the electric tokamak. It will all have a connection to the electric tokamak. Now, the electric tokamak, because of the designed structures of designed spaces inside the ship, and because of it being included in the overall weight of the ship, you will have two halves of a tokamak build put together, right? Put together in the ship. So one half of the ship will have a design space for a tokamak. The other half of the ship will have a design space of the other half of the tokamak. And when they come together as two shells, it builds the overall structure of the tokamak. Then all you've got to do is fill it with gas. And you fill it with gas. Now you need to understand that all these developed design spaces inside the ship are all hooked up to all of the structured design development of all of the light technology. So because of this build and because of the development of it, we're going to end up in manufacturing something that is very cheap, very affordable, and you don't have to include an awful lot of new weighted structures into the ship because it's already going to be there. And then the two halves come together, complete the build, and then all you do then is fill it with the minimal structures of technology and the minimal structures of all the gases that you need and are required. All the spaces for storing certain things like oxygen and storing certain things like various other structures are also going to be built into the shell of the interior. Built in, right? So they'll always be there and always be part and parcel of filling it with oxygen. Then we'll have areas of where this strengthened part of the ship has been developed and designed to be part and parcel of the compression rate. So we're going to have interior design spaces which are going to be designed for compression. So we'll be able to um, uh, vacuum compress the interior of the space. And because we can vacuum compress the interior of the space, we are able to compress all the gases of the air and all the gases of all the other products of, um, um, let's say, the exhaust of our mouth when it's captured and compress that gas into a structural safe area for scientific development. The oxygen that's in its compression unit that is also built into the ship, right? Remember, it's all designed spaces of design curves, of designed strength of bends and various other interior gaps and spaces. And it will all have special valves built into it, and it will all have special areas where you can fit the compression and vacuum exit. Let's say if you want an area which is that doesn't hold anything at all, and you just want to vacuum in there, you can suck all the air out, suck all the atmosphere out, and suck everything out until it's just a vacuum in space, or just a vacuum in a gap, right? So there's a whole load of things that are included in this development of shell technology. Now, because we can build lightweight and we can include all the necessary spaces in the structure of it, right? In the future, right, there is no reason why you wouldn't be able to print out a body of a spaceship if you had, let's say, a manufacturing developed printer of three-dimensional printing, right? At the moment, I'm working with materials and I'm working with powders and I'm working with clay and I'm working with shell kiln technology development as well, which is the tokamak, right? Kiln technology is the tokamak. Now, because we are doing and creating all of this, it also means that cheap, affordable manufacturing is also possible in the future. So you build a factory large enough to have a manufacturing printer available, and then all you do then is have a computer room and you type in your three-dimensional model and you type in all the structures that you require and need, and then you go to the factory floor. You then hit enter, and this thing prints every single thing that you require for your shell of ship, for your ship shell, right? And by the time it's complete, and it'll probably take, I don't know, several hours, right? 3 hours production of printing out the actual shell of the ship, right? Print it out, 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 and then stick it together, right? Manufacturing can build spaceships. And it can build spaceships under great quantity if it's required. And it can use all kinds of liquid, right, structures for printing. But at the moment, like I say, all we've got, or all I've got at this moment, right, is clay and powders. And we are clay powdering, and we are compressing, and we are kiln firing, and we are building and creating, and every single thing can be put to manufacturing. It's all affordable, it's all cheap, and it's all readily available for people to be able to develop, create, and use. So we'll leave it there because, like technology, with Michael Ian Hammond Eco is in development.